Hello, so in this video we are going to start talking through theme 1, which is representing data and understanding how data actually can be represented to other people. Now I'm going to start with this quote because I think it's a lovely quote, and it's from Nate Silver, which is from a book called The Signal and the Noise. And it says, "The numbers have no way of speaking for themselves. We're the ones that speak for them, and we're the ones that imbue them with meaning." Now, I'm not going to say too much about this. I'm just going to go through the next slides and hopefully you'll be able to form your own thoughts and opinions on what this might mean. So I'm actually going to start with a question that I get quite a lot when I teach this module, which is, what is the point of statistics? Now, I'm going to give you a few real life examples and show you some of the ways that statistics is used in the real world. Because ultimately, the point of statistics is that it can be conveyed. It's about conveying messages. Okay, and it's about telling stories based on evidence and based on data. So here is an example of the way which statistics are used in everyday life and why perhaps we need to be careful of them, why I need to train you to use statistics to be careful of these particular messages. So this is a 2011 London Underground advert. Now, just to give you a bit of context, in 2011 there were quite a lot of riots, nationwide riots, all across the country. And the vast majority of the rioters were deemed to be young people, so people between sort of 18 and 30. And as a result, they did a survey of the British public, and it came back that actually they thought that the vast majority of young people were violent and were kind of into crime and things like that. And so this was a campaign that was being run on the London Underground, where it said, and you can see down the bottom here, 99% of young Londoners do not commit serious youth violence. So in other words, saying, look, your misconceptions are totally wrong, right? You think that young people are these kind of violent people and they go out rioting and looting, but actually the vast majority of them aren't. They're not committing serious youth violence. Now actually this message is conveyed in a very particular way. It's something called positive framing. Now, positive framing is obviously putting things from a positive point of view. It's an optimistic point of view. It's saying, look, this is a good thing. 99%, the vast majority of young Londoners, they're not committing serious violent crime. However, I thought I'd also show you that I could take this exact same message and using same truths, okay, I'm not lying at all, I can show you this message from a negative point of view. And then you can maybe think about what message would have most impact. So a negative framing would be, well, not 99% of young Londoners do not commit serious youth violence, but to say that 1% of young Londoners do commit serious youth violence. It's the same figure, remember? 99% don't, 1% do. But one is a positive framing, one is a negative framing. Now, at the moment, you're kind of looking at this and going, well, 1% doesn't really sound that bad. So I can perhaps play with this a little bit more and make it sound a little bit more kind of threatening, okay? So let's have a look at this in a little bit more detail. Now, in 2011, there were about 1 million young Londoners, okay? So 99% of 1 million is 990,000, okay? But if I do the same thing with the negative framing, so the people that do commit the serious youth violence, well, 1% of 1 million, that leaves 10,000 young Londoners that commit serious youth violence, okay? So imagine instead that this was the headline, okay? If I'd said on that headline, 1% of young Londoners commit serious youth violence, this would probably be reaction, right? Well, so what? 1% is nothing, yeah? Who cares? Who is this guy? What is he trying to say, okay? Whereas if I say something like 10,000 young Londoners commit serious youth violence, suddenly that sounds a little bit more scary, and this is more likely to be your reaction. Okay? So it's all about how you frame it. And this is the point of statistics, really. Often the way which we interact with statistics is that end user. We're seeing these headlines or we're seeing these statements. And it's your job as a statistician to kind of question it and go, hang on a minute, what does this actually mean? Okay? Because often there's a hidden agenda or something which they're trying to get across. Okay, fine. Another example of where statistics is used, this is a more recent example in 2016. Hopefully you've all heard of Brexit. This is the campaign for the UK to leave the European Union. And this is quite a famous sort of image from the Leave campaign, the people that wanted us to leave the European Union. And it's the statement on the side of a bus. Now, actually, this has been shown now that it is not factually correct, but it said, we send the EU £350 million every single week. Let's fund our NHS instead. Now, the NHS is the National Health Service, and it's kind of, it basically allows us to have free healthcare, and everybody's entitled to that in this country, okay? So it's kind of trying to tug on those heartstrings. And obviously, vote leave, they're trying to get us to vote to leave the EU. And so as a result, they're trying to tug on our heartstrings, and they're trying to put this big number on that side of the bus, the £350 million, okay? And to most people, like if I said I have £350 million, that's a lot of money, right? A serious amount of money. But one thing I always ask my class to do is to make this number small, okay? What does £350 million actually mean in this context? And I kind of ask, and I get a few really good ideas. And then eventually somebody would say, well, hang on a minute, that £350 million is a population figure. In other words, it's taking into account everybody that lives in the UK, okay? That's what they all pay in collectively, £350 million. So to put this number in context, what we should be doing is comparing it to the size of the population size of the UK. Well, there's about 66 million people living in the UK, right? So if you take that £350 million and divide it amongst 66 million people, then each person is actually only paying in about £5.30 a week, okay? And actually you can make this number even smaller because that's per week. What if you make it per day? Well, if you divide this number by 7, you get about 76 pence every single day, which is about the same price a packet of crisps. So actually if you change the statement on the side of the bus to not say we send the EU £350 million per week, but to say we send the EU a packet of crisps every single day, do you think that has the same message getting across? Okay. Now, I'm not changed anything. This is still factually correct. We only send the EU a packet of crisps every single day, or the equivalent of a packet of crisps every single day. It's not changed the numbers at all. I've just simply changed the perspective from what it's put across. So positive versus negative framing. Okay. Another example of where statistics are used. This is on the front page of a daily newspaper, the Daily Express, okay? And it says that daily fry-up boosts cancer risk by 20%. Now, the cancer they were talking about here is pancreatic cancer, okay? And basically it's saying that a daily fry-up, by the way, a daily fry-up is like a breakfast with like bacon and sausages and eggs and beans and all sorts of things that are deemed fairly unhealthy and not very good for you. Not my favourite personally, but some people like it. And it basically said that if you have one of these unhealthy breakfasts every single day, it boosts the cancer risk by 20%. Okay. Now, what they're talking about here on the front of this page is something called relative risk. Now, relative risk effectively compares the group of people that don't have this daily fry-up to the group of people that do have this daily fry-up. Okay, and basically what it says is that 20% more people who have that daily fry-up every single day will get cancer compared to those that don't eat that daily fry-up. And the way to calculate the relative risk is simply by taking the new risk, in other words, those people that have that daily fry-up, and divide it by the old risk, in other words, those people that don't have the daily fry-up, and see what you get out, and you get 20%. Okay. Now there is another type of risk here. There's something called absolute risk. Now, absolute risk more deals with the absolute numbers or the actual figures. And the way to calculate it is simply by taking the new risk and subtracting the old risk. So the new risk, remember, are those people that have that daily fry-up, and the old risk are the people that don't. Okay? So relative risk, you divide those two risks, and absolute risk, you subtract those two risks. Now here on the front page, they're talking about relative risk. So what if I talked about absolute risk instead? Okay, well, if I go to the Cancer Research UK website, I find that just by pure chance, regardless of whether they eat pancreatic cancer or whether they eat daily fry-up or not, 1 in 80 people get pancreatic cancer, okay, just by pure chance. Now, what does that actually mean, right? Well, if I put 400 people in a room, and if these people, every single one of these 400 people, don't have a daily fry-up, okay, then I would expect 5 of them to get pancreatic cancer anyway, right? 1 in 80, yeah? That means 5 in every 400. So here's a room of 400 people in front of me. I'd expect 5 of them to get pancreatic cancer just by pure chance. So let's suppose these people do, these poor sods do, okay? Now let's go back to the front page. It says that there's increased relative risk of 20%. Now, what does 20% mean? Well, 20% means 1 in every 5, okay? So have a look. I had 5 people here in every 400 that do not eat a daily fry-up, and they would get cancer just by pure chance. Well, if I then look at people that do have a daily fry-up every single day, then 1 in every 5 just means that there's an increase of 1 from these original 5. So now I have 6 people who do eat a daily fry-up who will end up getting pancreatic cancer, okay? So basically the risk goes from 5 people getting pancreatic cancer who don't eat a daily fry-up to 6 people who eat a daily fry-up every single day who will get pancreatic cancer, okay? Now suddenly that increase by 1 doesn't seem so much anymore, okay? So that is 1 in every 400, okay, who will get pancreatic cancer. So comparing the old group to the new group, doing that subtraction, 1 in every 400, which is about 0.25%, and that is your absolute risk, okay? So your relative risk is 20%, and that's what goes on the left-hand side. Your absolute risk is 0.25%. Again, you can decide for yourself. They're both factually correct. One is looking at relative, one is looking at absolute risk. But which one has the bigger impact? Okay? So again, it's just about thinking about these things. Okay? Now we will look at these kind of ideas again before. So I can say, for example, I can now pose you a question. Is an increase of 1 in every 400 actually significant statistically? Okay? And we will look at that, and it's something called hypothesis testing, which will come along in theme 5. But I could also ask you the question, well, what other factors could cause this increase in risk? Okay, and that's all to do with like correlation and things. And that we'll look at in theme 6. Okay, so we will come back to these same ideas again, but this is just a sort of starting point, just being aware of how those statistics are put across and the types of messages. Okay. Now, I have actually come across a few more examples of this. So summer-born children are more likely to be diagnosed with depression than older pupils, right? The relative risk means that 30% more likely to be diagnosed with depression than older pupils. But actually, if you look at the absolute risk, it's only 0.2%, right? It's hardly anything. If you have a look at another statement, daytime naps once or twice a week may be linked to a healthy heart. If you look at the relative risk, you get 48% more likely, okay? But absolute risk is only 2.8%. And then finally, if you look at hidden fat raises a woman's risk of type 2 diabetes and heart disease with every 2.2 pounds, boosting her odds by 7-fold. Relative risk, 650%. Absolute risk, only 5%. Okay? So again, it's just about that positive versus negative framing. It's how you're putting across those statistics. I'm not saying that these are factually incorrect. Okay, so all of these sort of things on the front, these sort of statements on the front of our newspapers, they're factually correct. But you've got to be aware that they've been posed in a particular way to give across a particular meaning, and it may not necessarily be telling you all of the full story. Okay, so relative versus absolute risk, or positive versus negative framing. So finally, in summary, just for this particular part, we often need to make conclusions based on evidence in statistics, okay? That's really sort of at the heart of statistics. You go out, you collect some data, some evidence, and then you need to make conclusions based on that evidence. But we come across this data every single day, okay? So it might be, for example, needing to cross the road, okay? Or it might be choosing which jumper to put on, okay? And it's all based on evidence. You know, the things which we're wearing are usually based on evidence. For example, have we got to be somewhere nice today where we need to dress particularly smartly? Or what's the weather doing today? Is it particularly warm or is it particularly cold? These are all evidence which we can use to make conclusions. So we come across data every single day. Now, we also need to be aware that even if we come across data, for example, on social media or even in newspapers and things, it's very easy to manipulate that data, and we need to be aware of that. So as good statisticians, we need to be able to think critically to make these informed decisions so we're not caught out and we're not easily sort of swayed by these positive, negative framings or perhaps relative absolute risk, for example. Okay. Now, let's move on to a really key concept. So that was just a bit of an introduction to what statistics is all about. Let's move on to a really key concepts in statistics. And actually, on this slide here, I'm going to summarize everything that we're going to learn in the statistics part of this module, really the heart of what we're going to learn. Okay. So let's suppose we have a cake. Okay, your mum's made a delicious cake and it looks gorgeous and all chocolatey and got cream and strawberries and it looks absolutely delicious, right? And what we want to ask is this cake delicious? The cake looks nice, but does it actually taste nice? Okay. Now, my question to you is, do you need to eat that entire cake to answer that question? Okay, so is this cake yummy? Do we need to eat the entire cake in order to realise whether it's nice or not? Okay, and the answer is no, do we? Okay, the answer is we can just take a slice, and that slice is enough to tell us whether that cake is delicious or not. Okay, so if you eat that cake and it tastes really, really nice, eat that slice of cake and it tastes really, really nice, then that's probably going to be an indicator that the rest of the cake is pretty nice as well. Okay, so what we're really getting at here is this idea of a population versus a sample. Okay, the population in this case is the entire cake. Okay, it's what we want to understand. Does the entire cake taste nice? That's our population. Okay, whereas our sample is that little slice of cake, right? That little slice of cake that we're just going to taste to see whether we can understand anything about the population, in this case, the bigger cake. Okay, now, what we want to do is actually make an inference. Now, an inference is sort of understanding how these two things relate together. Okay, so if we can understand what's happening at a sample level, how can we then infer what's happening at a population level? How can we relate what's happening at a sample level to what's happening at the population level? Okay, so in this case, we taste the sample. Is it nice? Then we can infer whether the population, the bigger cake, is actually nice or not. Okay, now a few key words here. First one is a parameter. Now, a parameter is a characteristic of a population. Okay, so in this case, the parameter would be whether the cake tastes nice, the entire cake tastes nice. Another parameter may be the average weight of males, okay, or the average length of time that it takes somebody to complete an exam in the class. Okay, these are all parameters. Okay, they're talking about characteristics of a population, things which we want to find out from a population. Okay, whereas if we look at the characteristics of a sample, we call that a statistic. Okay, so it's really important to understand the difference between a parameter and a statistic. Parameter, we want to understand what's happening at a population level. Okay, for example, it could be the average weight of every male in the UK. Okay, now a statistic would be going out and collecting just a sample of those males, just a selection or a group of these males that live in the UK, and weighing those. Okay, and getting that average weight. That would then be a statistic. Okay. Now, obviously, we are looking at statistics. That's literally what this topic is called, okay? So statistics is all about trying to look at samples, okay, understanding the characteristics of those samples, and specifically how those characteristics, that statistic, infers information about the parameter, the population level, okay? So just remember, it starts with P, so population for parameter, and sample for statistic, okay? So population, parameter, sample, statistic, okay? They both measure characteristics, that's what we want to find. Population, parameter, sample, statistic. And we want to infer what's happening at the sample level will indicate what's happening at the population level, okay? Now, sometimes it is possible to go out and collect data about a population, an entire population. And if you do that, we call that a census. Okay, so a census is basically understanding what is happening at the population level. We collect data from the entire population. By the way, I used the word data there. A data is just simply like a number. Okay, so if I'm going out and taking a sample of people, let's say men, and I want to understand what is the average weight of men, okay, the data would be the weight of every single man. The statistic would be the average of all of that data. Okay. So yes, a data, perhaps in this example, if you wanted to keep with the analogy of my cakes, the data would be like each individual ingredient, like the currants and the chocolate and the flour and the eggs and the sugar, right? So the data would be each individual sort of ingredient, if you like, then they all come together to form the population, okay? Or the sample. Okay, fine. So I think we need to sort of understand what is sampling all about. Because really in this theme, what we're going to be doing is understanding the sample better. Understanding how the sample can tell us things about the population, okay, and how we can accurately make predictions about what's happening at the population level just purely from a sample level. So I thought I'd talk through a few different ways in which we can sample, okay? So some sampling methods. First things first, what is a population? Okay, well, a population is just a set of items that are of interest. Okay, and perhaps you might like to think of some examples. So I've just put some examples down here. Perhaps we've got some students enrolled at the college, or every chocolate bar of a particular type that's ever been manufactured. Perhaps it's citizens of the UK or birds of a particular species. These are all examples of a population. It's the big group. Okay, now most of statistics are trying to understand what is happening at a population level. Now we can actually understand, like I say, we can understand a population and we can measure them accurately using a census. So this is an example of the UK census, which is sent out every single 10 years, okay? And basically, you can see here that this is asking about what your ethnic group is, and you have to tick the correct box. And this is sent out to every single person in the UK, and they are required to complete it, okay? Now, the issue with censuses is that they are very expensive and they require a lot of work to distribute and analyse. So you have to obviously distribute them, then you have to take all that back in, and then you have to physically go through and find out a way of analysing this data. That's a lot of work, okay? However, they're very important, okay, because they can be used by government to make vital decisions. For example, how much budget should they use for healthcare? Or what about housing? Should they be thinking about building new houses? They need to give more budget to the economy there. Or even employment, okay? So they're really important to be used by the government, okay? They can also be used to make reliable predictions, okay? So in other words, you don't need to be running a census every day or every month or every week or every year, okay? Like I say, the UK census is run every 10 years because actually that's enough. We can make predictions because we understand how populations grow. We can make reliable predictions over the next 10 years just purely from this reliable census data, okay? However, censuses are great, but like I say, they require a lot of work and they can be very expensive, both computationally and physically cost, okay? So what we need to understand is that, so here we go, so it's too expensive, too much data to analyse, and it actually may sometimes destroy a population if you run a census, okay? For example, if you're trying to test the effect of a particular disease and you run that out over the entire population, you may end up destroying that entire population, okay, which is not what you want to do. So as a result, you come up with this idea of sampling, okay? Now, a sample is just simply a subset of a population. It basically means, okay, here is my entire group. I'm just going to take a piece of that. And that's what I would call a sample. Think of my cake analogy. The entire cake would be the population. A little sliver of that cake would be the sample, okay? So then what I want to do is analyze that sample. And then from that, I can make an inference. I can infer some information about what's happening at the population level. Okay, so another example of a population, if you didn't like my cake analogy, imagine I have a big tub of jelly beans, okay? That would be my population. And then from that, I can take a sample, in other words, like a handful of these jelly beans out, okay? So what kind of sampling techniques can we imply? Well, obviously samples are less expensive because they're smaller, okay? And they're easier to take than a census is, right? Obviously there's less data, so that's better. But of course we have to understand that they're usually less accurate because it's only a subset. We're not physically testing every single person in that population or every single item within that population. So because it's only a subset, it's open to a bit of variability, okay? And it's important in statistics when we're sort of analysing this to be aware of that. And we'll come up with ways in which we can overcome that over the next few weeks. We also need to be aware that we may not have enough data there to make accurate predictions, okay? So if we only take a small sample, there may not physically be enough data to make any kind of accurate conclusions from that. So really there are two types of sampling. Sampling boils down into two parts. We've got random sampling and then we've got biased sampling, okay? So let's look at each individually. Well, random sampling means that every member of the population has an equal chance of being selected. This is the best one, okay? Because actually this is probably the fairest way to get a sample, okay? If we just say, okay, everybody's got an equal chance of being selected. We're not just going to select people from this particular group and ignore everybody over here, okay? It means that everybody has an equal chance of being selected. Whereas obviously biased, well, bias does have its uses, okay? It's usually used if, for example, if it's a pilot or if data is limited or not freely available. It's not as good, okay, but sometimes it will do, okay? If you just want to kind of get an indicator and then perhaps you want to run a proper sample using random sampling later on. So I just thought I'd quickly talk you through the different types of sampling which you can have. So these are all types of random sampling. So the first is simple, okay? Now that just simply uses some random selection method. So for example, if you assign everybody a number, okay, and then you use a lottery, okay? So for example, like balls or something, and just pick them out of a hat, and you say, right, okay, this is a way of just randomly choosing those numbers and say, right, number 5, number 7, number 13, number 46, number 23, and then you're basically selecting people this way using some kind of random number generator. Okay, now that ensures that every member of the population has an equal chance of being chosen. Another way is systematic sampling. Now this basically means that you choose members of a population at consistent intervals. For example, imagine you wanted to sample a demographic from a shop. So perhaps you want to go into Sainsbury's or some sort of famous supermarket, and you want to understand the shopping habits of these particular people that shop in this shop. Now obviously you're not going to choose every single person. That will be the population. So what you might do instead is sit by the door and count every 5 people. So 1, 2, 3, 4, 5, I want you. 6, 7, 8, 9, 10, I want you. 11, 12, 13, 14, 15, I want you. And so on and so on and so on. So you're basically choosing every 5th person. So this is also an example of random sampling methods. Okay. Another one is stratified sampling. Now stratified sampling is all about putting the population into groups and then randomly choosing the same number of people from each group. So an example of that would be in the college. Okay, each college has got different classes. Okay, and it might be, for example, that providing you go around to every single class and you might select 3 people from every single class. Okay, well if there's 10 classes in the college, that means that you end up with 30 people and you end up with a fair proportion from every single class within the college. Okay, so that's an example of stratified sampling. Okay, or for example 5 people from each age group or something like that. Okay. Last one is cluster sampling. Now, cluster sampling is very, very similar to stratified sampling in the sense that you're using groups and then choosing a random sample from each of those groups, except those groups will be naturally occurring. So for example, if you're talking about population of the UK and you're interested in measuring things about the population of the UK, then you might select people from their naturally occurring geographic locations. In other words, where do they live? Okay, and then you select a random sample from each of those locations. So finally, let's just have a quick look at the other type of sampling methods, which is the bias sampling. Okay, now there's 2 types. First one is quota sampling. Okay, now all you literally do is you just basically create groups before you start the sampling. And so, for example, it might be I don't know, sort of people of each age group. Okay, then as they come through the door, all you simply do is say, right, how old are you? Right, 13. Right, you go in that group. How old are you? 5. Right, you go in that group. How old are you? 10. Oh, well, I've already filled the group for 10, so I'm just going to ignore you. Okay, so you basically just fill them. It's like the first past the post example, where basically you just have these bins. Then as people come, you just fill the bins. Okay, and if that bin is full, you just ignore them. Okay, so you just basically keep going until each of these quotas are full. The other type is just the opportunity or the convenience sampling. Now that's just simply you go up to the first however many people you meet. Okay, so for example, you're walking along the high street, you need sort of 10 people to survey, you just find the first 10 people you meet. Okay, don't worry about whether they're random, they could be all from the same family, they could be different, it doesn't matter. Okay, this is just opportunity, it's just finding the first people that you find, that you walk up to, and then you just collect data from those. Okay. Now, like I say, bias sampling does have its uses, particularly if there is, random sampling just can't be done. Okay. So, for example, if you're doing a pilot study or if you're just trying to get an idea of what type of data might be out there, then you might do the data for real or collect the data for real later on and put time and effort into properly studying for this. Then fine, bias sampling is okay. Okay. All right, fine. So, can you think of some examples of sampling in real life? Now, it is used everywhere, okay, and I thought I'd just show you a couple of different examples. The first is through television viewing figures, okay? You might see, for example, on social media or in the news or something and say, 6 million people watched this television program last night. Now, actually, they don't have that data because the way that it's collected, I mean, if it's online, it's slightly different. They do kind of have that data, but actually they just don't use it. But particularly if you're watching television, okay, there's no way of telling how many people are actually watching that particular signal because it's just a signal that is just thrown out to people. Then people just hop onto that signal through their aerial. Okay, so there's actually no way of being able to determine how many people are accessing that particular television signal at any one time. So the way they do it instead is using Barb. Okay, and what this is, it's a sample of about 10,000 people. They're paid for it, and they basically have to log what they're watching. Okay, so sitting there watching the television, they have to actually log what they're watching, and there's a device that connects to their box and to their phones and things. And they basically collect data from this sample and understand how they're interacting, what they're watching, and how they're interacting with things like on-demand services. And then from that sample, you can make then inferences about what's happening at the population level. Okay, so that's one example of where sampling is used in real life. The other example is through exit polls. So in the government, sort of around election time when you're electing a new government, the ballot boxes, so the time when you can vote up to is 10 p.m. So basically anything beyond 10 p.m. you can't vote. But then usually what happens at 10 p.m. is an exit poll is released on the television. Now what this exit poll basically is, it's people standing at every single polling station around the country. And they basically just ask random people and say, who did you vote for? Who did you vote for? Who did you vote for? It's completely anonymised, okay? But basically just by having that data there, they're then able to make an inference about what the final result is going to be. And usually it's pretty accurate, okay? Now, obviously it's got the number of seats which they're expected to gain. Usually the seats will vary slightly, like by a few, but it's actually, you know, if it's a Conservative majority, a Labour majority, a Lib Dem majority, it's usually pretty accurate from that sense. So it's able to predict who's going to win that result before the results have actually been counted, okay? So that's an example of sampling there. So finally, sampling, this is really important. We nearly always want to understand what's happening at population level, but censuses we can't do very often, okay? So it's very hard or impractical to collect data from a population. So if we're collecting data from an entire population, that's called a census, they're hard, they're impractical, they're expensive, okay? So what we do instead is use sampling. And then we hope that that will tell us something about what's happening at the population level. And what this course is all about is understanding how a sample will infer something about a population and the types of things we need to be careful of. Okay? So we need to be aware about how we can approximate a sample from a population. So let's move into actually how we can represent data a little bit more then. Okay? Well, one way of representing data is through something called a box plot. Okay? So what a box plot literally does is it's a way of visualizing the spread of data. Okay? And it literally just divides your data points. So you put your data points into order, and then you divide them into 4 equal parts, okay? And then from that, you can visualize the central value, and you can also visualize how the data varies within a data set, okay? So you can see here that these vertical lines, 1, 2, 3, 4, 5, they represent the positions of particular points within the data. So the first one is the lowest value, the top one is the highest value, the one in the middle is the middle value of that data set, and then the one each side of that middle value are called the quartile values. Okay. Now it's important to understand these two concepts down here. It's a measure of variability. So you have range. Range is just simply, well, what is the difference between the highest value and the lowest value? Okay. So understanding how spread out, what the difference in the extreme values are. Okay. The next one is interquartile range, which is the upper quartile subtract the lower quartile. So in other words, it's just this little bit in the middle here, okay? Now the reason why you might want to look at interquartile range relative to, for example, just the straight range, is that if you have outliers in your data, now outliers are just particular values which may lie way outside the general trend of where your data is, where the bulk of your data generally lies. If you have outliers, then obviously your range is going to be way skewed out, okay? Whereas the interquartile range will kind of give you information about the middle 50%. So you see here, I've got 1, 2, 3, 4 regions within my box plot. Now the reason why I put a box around the middle 2 is because this is the middle 50%. This is where the most reliable data is. If there's any outliers, chances are it's going to be in the outer 25%. So either up here or down here. Okay, so sometimes looking at the interquartile range is more relevant, particularly if you have outliers in your data. Okay. Now, there is a test to see whether there is outliers in your data. In this course, it's measured by saying 1.5 times the interquartile range. Okay. So remember, the interquartile range is just that middle 50%, the difference between these this value and this value, the upper quartile and the lower quartile. Okay. Now, if there's an outlier, it means it will lie less than 1.5 times the interquartile range below the lower quartile. So in other words, if you take the lower quartile, you take however big the 1.5 times the interquartile range is, okay? And if you take that away, if there's any values that lie outside that range, it means there's an outlier. And similarly for the to the right, if you look at the upper quartile and if you add on 1.5 times the interquartile range, if there's any values beyond that value, then you can say that those are outliers, okay? So box plots are really useful, okay? If you want to compare a box plot, you should include both of these. You should include a measure of central tendency. Now we'll look at measures of central tendency in a little bit, but effectively it's just an average, okay? Mean, median or mode, right? So you should include some measure of central tendency. Where's the center of my data tending towards? You should also include a measure of spread. In other words, how spread out is my data? Now, you have to ask yourself two questions. So if you're looking at which measure of central tendency to use, you need to ask the question, are there any outliers in your data? If the answer is yes, you must use the median, okay? Because the median won't get skewed by outliers, and we'll look at this in just a second. If the answer to that question is no, then you need to use the mean, okay? So if there are outliers in your data and the answer is yes, use the median. If there are outliers in your data and the answer is no, use the mean instead, okay? Because the mean will always be skewed by outliers, okay? If you're looking at what measure of spread to use, so when you're comparing your box plots, you need to ask the question, are there any outliers in your data? If the answer to that question is yes, use the interquartile range. Remember, the interquartile range gives you the middle 50%. Okay, so if there are any outliers in your data, they'll always lie in those outer 25%. Okay, so 25% at the top, 25% at the bottom. Okay, so the interquartile range will basically remove any outliers. Okay, if there's no outliers in your data, you're fine to use the standard deviation. Okay, and we'll look at what standard deviation is later on. So just for the moment, bear this slide in mind. It might make sense to just make a quick copy of this slide so that you've got it there for later. Okay. All right, fine. So maybe you could have a go at creating a box plot from the following data set. And is there any evidence to suggest outliers in your data? This is the question that I want you to have a go at for homework, okay? So please make sure that you have a go at this question here for homework, okay? And upload it for Flipgrid, like I've shown you. So just simply to have a go at slide 36, create a box plot for this data set. And can you say whether there's any evidence to suggest outliers in your data, okay? Now, let's move on to histograms. Okay, so I'm just going to open up this link here. So what is a histogram? Well, a histogram is a way of showing the distribution of data. Okay, so a histogram is a way of showing the distribution of data. So you can go to this GeoGebra page here. This is my GeoGebra site. Okay, and if I just bring this across, and I can show you what you should see if you come on here. Okay. So this is what you should basically see. Now, if I make this full screen as well. Okay, so this is basically what we've got here. In fact, I'm just going to exit out of that. Okay, this is basically what we've got here. Okay, so we've got some data up the top here. Okay, and I can move these data points around. So these are basically data points. These dots represent data points. And I can position these data points whatever I like. Okay, so for example, I've got quite a lot of data points. I've got one data point which is 0, 2 data points which are 1, 3 data points which have a value of 2, 1 data point with 5, and I can basically move these around and vary them however I like. Now what I want to do, the whole point of a histogram, is that I can divide this data up into bins. Okay, now you can see, just focus on the left hand side for the time being, you can see that I've divided the data up into bins. Okay, so the first bin is from 0 to 2, the next bin is from 2 to 7, the next bin is from 8 to 9, next bin is from 10 to 20, okay? And I can see where these bins are, okay? Now, if I make the bins all equal width, okay, so let's make them all, how many bins have we got? 1, 2, 3, 4. Let's make them all 5, okay? So next one will be at 10, next one will be at 15, okay? So if I make them all equal width, like so, if I make them all equal width like that, in fact that one's too far over. Yeah, so if I make them all relatively equal width, then this will be basically a bar chart. And this is what I've got on the right-hand side. So I'm just going to hide me for the time being. Okay, so this is what I've got on the right-hand side. It's just simply a bar chart, okay? And the bars, the height of the bars correspond to how many things occur in that bin. So have a look. This is my first bin over here on the left-hand side, okay? And I have 1, 2, 3, 4, 5, 6 data points lying in that first bin, which means that I've got 1, 2, 3, 4, 5, 6 data points here. Sorry, that data point should be there as well. Yeah, that's better. So there's 7 data points. Sorry, that data point is over here. Okay, so yeah, so I've got 7 data points in my first bin, which means the height of my bar is going to be 7. Okay, you notice that the width of my bar corresponds to the width of this bin, and so on. So the next one, the next bin only has 1 thing in. Okay, so the height of that bar over here is only 1. Next bin has 1, 2, 3, 4, 5 things in, so the height of that bar is 5. And then the last bin only has 1 thing in. So basically what I'm trying to do here is compare these 2 things together. Okay, so this is a frequency plot. Okay, And basically the width of the bin corresponds to the width of the bin over here. So the width of the bar corresponds to the width of the bin over here. And the height of the bar corresponds to how many things are in each bin. Now if I just refresh that to take it back to how it was, okay? So if I make the bins different widths now, okay, then I've still got on the right-hand side the height of the bin corresponding to how many things appear in that bin. So the height of this bar over here is 6 because there are 6 things which appear in this bin over here, okay? Now, at the moment, this isn't fair, is it? Because have a look. At the moment, it's saying that the first and last bin have exactly the same number of data points in them, okay? Which is true. It is true. But I don't think that this is the fairest way to represent this data. And the reason why I don't think it's the fairest way is because the bins are of different widths. Like, have a look. The first bin is only 3 wide, whereas the last bin is 10 wide. So the fact that they've got the same number of things in, I need to represent the width of the bin on here somehow. So the way which I'm going to do this is using the frequency density. Okay, the frequency density. So the frequency density just simply says how closely packed together are these data points. So obviously the bin with the first bin, the data points are really closely packed together. There's still 6 data points in there, but they're really closely packed together, which means that the frequency density should be far higher. Whereas the last bin, the data points, there's still 6 data points in here, but the data points are much more spread out because there's a wider bin, okay? So therefore the frequency density should be much lower. So the way to calculate frequency density is to take the frequency and divide it by how wide that bin is. So it basically says, assume that all of the bins were width 1. How many things would be in that bin? So let me say that again, because that's really important. The frequency density says, assume that each of these bins were of width 1. So they only had width of 1 thing wide, okay? Then how many things would be in that bin, assuming all the data points are equally spread? So if you have a look at the first one, there are 6 things in that first bin, and the bin is 3 wide. Which means that if the bin was only 1 wide, there'd be 2 things in that bin. Whereas if you have a look at the last one, there's 6 things in the bin, but the bin is 10 things wide. So if the bin was only 1 wide, then there'd be 0.6 things in each bin. So the way to calculate frequency density is by taking the frequency and dividing by that class width, dividing by the width of that bin, okay? So now if I come over here to where I've got my frequency plot, instead of plotting the height of the bars which correspond to the number of things in that bin, what I'm going to plot instead is the height of the bars is going to correspond to the frequency density. Okay? And now you can see this is a much fairer plot, because have a look at the first bin relative to the second bin. Okay? Notice that the width of the bins, so the width of the bars, still correspond to the width of the bins. Okay? But now the height of the first bin, or the height of the first bar, is much higher because there are more things closely packed together. So there's still 6 things, but they're closely packed together. So therefore that frequency density is higher. So the frequency density is 2. Whereas that last bin, the frequency density should be 0.6 because there's 6 things in the bin, but they're more spread out because their bin is 10 wide. So therefore it's only 0.6 high. Now I think this is much fairer way of representing this data. Now here's my question to you. So if I come back in now, here's my question to you. How could I get the frequency back from this graph here? So this is a histogram, okay? This is a histogram, okay? How could I get the frequency? How could I work out how many things are actually in this bin? So imagine I didn't have this information over here on the left-hand side. If I just looked at this histogram, if I looked at that first bar there, could I tell you that there are 6 things in that bin? Well, yes, I could. Because look, I know that the bin has got to be 3 wide. Okay, that's telling me that along the bottom. So the bin is 3 wide. That's the width of the bar. And if I know that the height of the bar is 2, that's the frequency density, I'm basically saying, well, if the bin was 1 wide, there would be 2 things in that bin. That's what the frequency density says. So now I know that the bin is 3 wide, then there must be, well, 3 times as much in that bin. So instead of there being 2, there must be 3 times 2, so there should be 6. So the way to work out the frequency from the histogram, if you've got frequency density on that y-axis, is by multiplying the base times the height. In other words, calculate the area, okay? So it's the area that tells you how many things are in that bin. So hopefully that makes sense, okay? Okay, cool. So let's have a look at this now. Okay, so let's have a look at the next one. Okay, so this just really summarizes exactly what we've just said. To calculate the frequency density, you take the frequency and divide by the class width. A histogram groups the data into classes, and the frequency or the amount of data in each group is shown by the area of that histogram. Okay. Another way of representing data, and a really useful way, is through a scatter plot. Now, this is particularly useful for what's known as bivariate data. So variate just means change, and bi means two. So if you have two variables that change in relation to each other, for example, time and height of a person, okay? As you get older, okay, your height should also increase. Those are bivariate data. One variable is time, the other variable is height, and it should change in relation to each other. We will look at this in more detail in theme 6, but effectively that's one other way of showing it. So along the x-axis in this case we've got year, and on the y-axis we've got the age of a particular victim that was being killed, and this will be an example which we'll come up with later. Okay, so it's really useful for showing how one variable changes in relation to another. The variable along the x-axis is the independent variable, and the variable on the y-axis is the dependent variable. It should always be that the independent variable is usually the thing which you control. Okay, it's usually the thing which you are changing. Okay, then the dependent variable is the thing that changes in response to this thing changing. So in this case, the year is the thing changing, that's the thing we're controlling. Okay, then the age of the victim is the thing that changes in response to that year. But we'll look at that in theme 6. Okay. All right, fine. Let's quickly skip through this. So I just quickly wanted to recap the measures of central tendency. Now, a measure of central tendency is just another word for that is an average. Okay, isn't this just an average? So a measure of central tendency is an average. It's basically saying, here is a data set. Find me the best representative of this data set that you possibly can. So I kind of think of this almost like a prime minister. Imagine a country, okay, of let's say the UK, okay, 66 million people. This is our data set, 66 million people. Each individual person is our data, okay, and that's our population. And what I want to do is pick out one thing that represents that data, okay. I want to find a representative of that data. So it's a bit like the Prime Minister. It goes forward and they represent the entire country, okay? That's literally what a measure of central tendency is getting on with. It's an average, okay? The reason why it's called central tendency is the average is usually where the center of your data tends towards. And if you're familiar with the notion of normal distributions, which we will meet in theme 3, then this will be a little bit more familiar. It's like, okay, the most things should occur roughly in the middle of a data set, okay? Okay, so let's actually have a look at the different types of central tendency that we can have, okay? Well, first things first, let's actually talk about what each of these different things mean, because these are really important words. First thing, variable. Now, a variable is just simply the characteristic of a study. So, for example, if you imagine my jelly bean example, if I have a jar of jelly beans, okay, the characteristic might be, well, how many things actually appear in this jar of jelly beans? Then you've got two types of variables here, okay? So you've got a discrete variable versus a continuous variable. So a discrete variable means that something can occur at fixed values. So I said integer values, it usually is integers. Not strictly true, it should be fixed values, okay? So for example, you might have shoe sizes. Shoe sizes only occur at fixed intervals, okay? So for example, you have a size 2, or a size 2.5, or a size 3, or a size 3.5. You don't have, for example, a size 3.1 recurring. So it's a discrete variable because it occurs at fixed values. Whereas a continuous variable can take any value, okay, within an interval. Okay, so if you like, there's no gaps between the values. Then from that, then you can have two other types of variables. So you can have a quantitative versus a qualitative. Now, if you're a quantitative variable, it means you're dealing with numbers, numerical values, okay? And actually another word for a quantitative variable is a numerical variable. Whereas qualitative is usually stuff to do with words, okay? How are you feeling today? Happy, sad, miserable, crying. You know, these are all qualitative variables because they're dealing with text, okay? Another way of dealing with, another name for qualitative variables is categorical variables, because they're usually variables that can be put into categories, okay? Then finally, we've already discussed this, a population is the entire group, and then a sample is a part of that group, a subset. Okay, so let's actually look at some data then. Okay, and let's actually look at the different types of average that we can have. So the different types of average are mean, median, and mode. So it all begins with M. mean, median and mode. And they're known as measures of central tendency. And they literally measure where does the center of that data tends towards. So let's assume that this is the data and we've kind of visualized it either as a dot plot or as a histogram or as a box plot. We're basically saying where does the center of that data tend towards. So in this case, the center of the data is probably about there, probably around the sort of 2000 mark, okay? So this would be an average. It's the best, if you had to choose one value from all this data set, okay, if you had to choose one value, an average value, what would that value be? That's your measure of central tendency, that's your average, okay? And there's three types, there's a mean, median and mode. Now this is really important. People think that an average is just a mean. It's not. There are three types of averages. You've got a mean, you've got a median and a mode. These are all averages. And we'll talk about why we have three later on, okay? And it's all to do with the fact that sometimes one measure will be better than the other, okay? Okay, so these are all examples which I'll get you to go through in the class. Okay, fine. Okay, so let's now start talking about measure of central tendency and also that's effect on skewness, okay? Now, skew is all to do with if a data is non-symmetrical, okay? In other words, most of the data is like bunched up down one end. So skew is all to do with like where is the majority of the data bunched towards. So if you have data bunched towards one end, for example, the left end, and there's a few over towards the right, that would be an example of skew. Okay, so here we have an example of skew. Okay, the majority of the data is skewed over here on the left hand side, then there's only a few which are left over here on the right hand side. Okay, so in order to work out where the mode of a histogram so mode is always the most common value within a data set. Okay, and from a histogram you can infer the mode by simply looking at which one has the highest peak. So which bar has the highest peak? That will be the most common one. Because if you think, the height of the bar should correspond to either frequency or frequency density, okay? So the height of the bar should tell you where the most common value of the data is, the one with the highest frequency, and that should tell you the mode. So to infer the mode from a histogram, it's just simply the bar which has the highest peak. If you want to work out the median from a histogram, it's the middle value in an ordered data set. Now, just a quick thing, why is it n+1/2? Okay, so to work out the mode of the median of a data set, why is it n+1/2? So let me just show you this. Let's suppose I have a set of numbers. Let's suppose I have like 3, 5, and 7. Well, where would you say the median of this data set lies? Remember, median sounds like medium, it's in the middle, okay? So in this case, the median value is 5, okay? So that is the median value. Now just having a look at this, how many data points are there? Well, there are 3 data points. Okay, now most people say, well, okay, in order to work out where the middle value is, surely you just take the number of data points, in this case there's 3, and divide it by 2. Okay, well, if you get 3 divided by 2, you get 1.5. In other words, the median value should lie halfway between the first and the second value. That's not correct. Look over here, okay? The median value should occur at the second position. Okay, so the second value in this data set of 3 points should be the middle value. Okay, so what you're going to have to do here is adjust this formula. And the way to adjust the formula is before you divide by 2, you need to add 1 to the number of data points. Okay, and that will then give you 4 divided by 2 or your second position. Let me show you with another example. Okay, let's take 1, 5, 6, and 7. Okay, the median value in this case should lie halfway between there and there. So slap bang in the middle should be halfway between the second and the third. So actually in this case, the median value will be between 5 and 6. So halfway between 5 and 6 is 5.5. Okay, so that's where the median value should lie. Okay, and just be aware that should be, well, it's the halfway between the second and the third position, so the 2.5th value. Okay, so let's check it. How many data points are there? Well, there's 1, 2, 3, 4 points. So if I say, well, okay, the median value should occur at the 4 plus 1 divided by 2th value. Well, 4 plus 1 is 5 divided by 2. That's the 2.5th value. Okay. So always be aware, in order to calculate the middle value of a data set, the median value of a data set, it should be the n+1/2th value. Don't forget to add 1. Don't just divide the number of data points by 2. Okay. If you wanted to find it from a midpoint, well, notice it's the middle point of the distribution. So the middle point should just be, where is the middle of that distribution? And do it by area. 50% of things should occur on this side and 50% of things should occur on this side. Okay, so remembering the area corresponds to frequency, okay, because it's a histogram, okay, because on the y-axis there should be frequency density, so the area should correspond to frequency there. Basically 50%, in other words, half of your things should occur on the left-hand side, half of your things should occur on the right-hand side, therefore the median value should be slap bang in the middle, okay, at the halfway point. Okay. If you wanted to find the mean of the histogram, you need to be a little bit more adventurous, okay? It's basically saying if all of the values were the same, what would that value be? That's the definition of a mean. If those values were all the same, what would that value be? Okay. If you wanted to infer it from a histogram, it would be where is the balance point? And notice that the mean is always influenced by extreme values. For example, up here we've got quite a lot of extreme values, values that lie outside the general trend of the data. General trend of the data is down here, right? The kind of extreme values are up here. So the mean will always be influenced towards those extreme values, all right? And we'll explore this more in the class next week. So if you have a look, if I try to think of this as a balance point, the mean will be about there. Imagine this as sort of a seesaw, right? So if this is a seesaw, where would the histogram be balanced? It would be balanced around there. If I had more extreme values, the mean would be further towards the right, because that's where it's going to be balanced. So just think, okay? Just think. The mode is just the highest peak of the histogram. The median is the halfway point. 50% of the area on the left, 50% of the area on the right. The median is the one in the middle, okay? The mean is the one, if you imagine this histogram as a bit like a seesaw, where would that balance point be? All right. So we're going to go through this in class, but effectively we will kind of play around with this and we will realize that the mean is always, always, always skewed by outliers. All right. Now this is an activity which I'm going to get you to go through in class as well. Okay. Now just to finish off then, let's have a look at the different types of variables that we can have. Okay. Now I've said before, in the kind of couple of slides ago, that there are two real types of variables. You have the numerical variables, and then you have the quantitative variables, or the categorical variables, okay? So there's two different names. Numerical is quantitative, think quantity, okay? A quantity of something is a number, okay? And categorical, things that can be put into categories, usually done by text, so qualitative, okay? Or qualities. So we can basically divide these up into more details. So let me give you an example of a numerical variable. They're literally values of data which represent counts or measurements. So for example, an age of somebody, that's a measurement, isn't it? Or a height, how high are you? Or what is the length of something? Could be length of time, for example. These are all examples of quantitative or numerical variables. Whereas on the other hand, a categorical variable are data which represent groups or categories. Okay, so in other words, the data can be put into groups or categories. So gender, okay, you're male, you're female, or you're other. Okay, eye color, blue eyes, brown eyes, green eyes. Okay, you can all put these people or this data into specific categories. Okay, so it's important to be aware of the difference between categorical numerical variable and a qualitative or categorical variable. But we can also subdivide these two variables down as well. So if you look at the numerical or the quantitative variable, we can divide it into either an interval or a ratio variable. Now be aware here, the difference is quite subtle. Okay, so an interval variable is basically data that will result in a meaningful interval or a range of values. So for example, what is your body temperature? That can result in a range of values. For example, my body temperature is 37 degrees, or my body temperature is 38.2 degrees, or my body temperature is 36.5 degrees, okay? It will all result in a range or an interval of values, okay? Another example would be, what is your credit score, okay? Whereas a ratio variable, very similar to an interval variable, it will still result in a range of values. However, and this is the key part here, 0 means that that variable does not exist. Okay, so here, if you have a body temperature of 0, I mean, you'd be probably dead, but if you do have a body temperature of 0 degrees, you'd still exist, right? So you can still have 0 in an interval variable. Whereas with a ratio variable, if you get 0, it means that that variable does not exist. So for example, how old are you? If you have an age of 0, it means that you do not exist, okay? Same with height. If you have a height of 0, it means that you do not exist, okay? Because you have to physically have some height. So just be aware of the difference between interval and ratio variables, okay? An interval variable is a variable, a quantitative variable or a numerical variable that results in a range of values. Whereas a ratio, similar kind of idea, but if you get 0, it means it doesn't exist. If you look at categorical variables, they also can be subdivided into two subcategories. So you can have nominal variables or ordinal variables, okay? A nominal variable, we'll think of the word like nombre or nom. It means name, okay? In this case, it's named categories, okay? So the data can be put into categories, but there's no real natural order within that category. So for example, if I said to you, what gender are you? Well, you could be male, you could be female, you could be other, but I can't really order you in any kind of sensible way. So it doesn't make sense to have male first, then female, then other. I could equally have female first, then male, then other first, then male, then female, and so on, okay? So basically, the data can be put into named categories, but there's no real order associated. Whereas the ordinal, and the clue's kind of in the name, the ordinal variables means that the data can still be put into categories, because it's a categorical variable, but there is some kind of natural order that comes out of it. So for example, do you like statistics? And you can order that from not at all, somewhat, to very much. Okay, so there's some kind of natural order that you can get out of it. So these are the different types of variables that I want you to be aware of, okay? Now, this is really important when we look at measures of central tendency, and perhaps you can sort of start to think about when each type of measure of central tendency is going to be used, okay? If you're looking at nominal variables, okay, the mode is the most useful. So remember, the nominal variable are the data that can be put into categories, but there's no kind of natural order, okay? So in this case, you just simply want to look at the mode. Which category has the most things in it, okay? The ordinal variables, just remember the ordinal variables can also be put into categories. However, there is some natural order that occurs from those categories. So for example, do you like statistics? Yeah, not at all, somewhat, very much, okay? So because there's some kind of natural order that will occur, we can also look at the median here. Okay, so you can look at mode, which category has the most things in, that also is still valid, but you can also look at median because you have some kind of order to those variables. In other words, you can look at which one comes in the middle, okay? Now, if you look at the numerical variables, so either ratio or interval variables, you can look at two types. Is it symmetrical or is it skewed? Okay, so is the data nice and evenly spread out, or is it actually all bunched up towards one end? Okay, so symmetrical is nice and ordered, it's nice and evenly laid out. Okay, well in that case you can use all three. Any of those will count. And in actual fact, as we will see later on with something called the central limit theorem, it should be the case that with numerical variables that are symmetric, those three measures of central tendency should actually all be the same, okay, as the number of data points increase. However, if you're dealing with skewed data, in other words, all the data is bunched up towards one end, well, in that case, you can only really use the median. That's the only real sort of reliable measure of central tendency that you can use, the one slap bang in the middle, okay? So maybe you might want to have a go at these in your own time, okay? In fact, we'll go through those in the class. And then just to finish off, measures of central tendency tell us one value that represents a data set, okay? There are three measures, mean, median, and mode. They are all types of average. So measure of central tendency, another word for that is an average. And there's three types, mean, median, and mode. You need to know how to calculate all three and what they show, okay? We've also just looked at when each one is most useful, okay? So be aware, you've always got to think, what type of variable am I working with? And that will dictate which measure of central tendency you should use, okay? And the factors that affect our measure of central tendency is obviously the skew, as we saw in that last one. So if it's a numerical variable, is it symmetric? Are the data points nice and even? Or are they actually bunched up to one end? Are they skewed? And we also need to look at the type of variable as well. Okay, so hopefully that makes sense. Okay, please remember to do that task which I set you with the box plot. Okay, and please upload it to Flipgrid before the end of next lesson. Okay.